Module D, lecture 9. In this lecture, we shall discuss about another type of synthetic model called as intervening opportunity model. In lecture 8, we discussed mainly about the doubly constrained gravity model. What is really doubly constrained gravity model? What are the flow conservation constraints, how we use the balancing factor, then the classical version of the doubly constrained model, and then we took an example to explain you how this model can be applied. Then we also talked about the advantages of gravity model and some important considerations which one has to keep in mind, because otherwise they may act as a limitation or disadvantage of the doubly restrained model. So, with this background, today we shall discuss about another synthetic model, but before I proceed further, I would like to briefly discuss about the various types of trip distribution model within the different categories. Already we discussed about this, what is singly constrained model, what is doubly constrained model, okay. But I will once again like to briefly mention and then talk about the intervening opportunity model. Trip distribution model may be unconstrained also. So far we have not mentioned this one, we mentioned only singly constrained and doubly constrained, but it could be unconstrained. That means, where we shall not satisfy this T I j sum over j equal to P I. So, you take the cells of a trip distribution matrix, add all the cells in a row, that should give ideally the production. That constraints will not be satisfied automatically by the model. Also the attraction constraints, that means, if I take a column in the trip distribution matrix, then all the cells in a column, if you add, that may not give you A j automatically, based on the model form or model equation. So, once none of these two constraints are satisfied, or none of these two constraints is satisfied automatically by the model form, then we shall call that model as unconstrained model. That means, row total, column total, both ends, right, will not be satisfied automatically by the mathematical formulation of the model. So, then we shall call it as unconstrained model. Then the total interaction constraint model means, there the model will ensure, all these have to be anyhow ensured, right, but the question is that whether the model form will ensure this or not, right. So, the model form in this case will ensure that sum over P I, sum over all zone, the total productions from all the zones should match with the total attractions of what the zone, all the zone. So, sum over P I, sum over I should be equal to sum over A j, j means all the destination zones, so sum over all destination zones. So, generally as T I j equal to alpha into P I A j by d I j to the power n, that is the general form. So, in this case alpha will be equal to, as I have written here, sum over P I, sum over I divided by sum over I, sum over j P I A j by d I j to the power 2 or d I j to the power n in general. And same way, this is equal to again sum of the A j for all the destination zones divided by sum over I, sum over j P I A j d I j to the power 2 or d I j to the power n, as the case may be. So, then it is called that the total interaction constraint model. So, model ensuring that that is what is happening, right. Then singly constraint model, which may be again production constraint model, that means only the T I j sum over j should be equal to P I, that will be ensured automatically by the model form. And in attraction constraint models, only T I j sum over I equal to A j, that constraints will be met, the other one will not be satisfied automatically. And doubly constraint model is something where both the constraints will automatically get satisfied by the model form itself. Okay. So, with this now let us talk about this intervening opportunity model. What is intervening opportunity model? Now, this was originally actually proposed by Stafford, and the basic premise is like a trip will remain as short as possible, lengthening only as it fails to find an acceptable destination nearer in hand. I think two examples I could remember immediately. One is maybe there is a cyclone or hurricanes and some kind of natural calamity like that, and such kind of things will pass through certain areas. So, people need to be maybe evacuated, right. So, where you want to take them? Would you like to take them to a far distant place? Probably the answer is no. We would like to shift them maybe if possible, and if there is a suitable location of course, then maybe immediately to the next village, right, which is just outside this area, or if a suitable place is not available immediately outside that influence area, then you try to take them little away. So, you will only take those people away, right, when you do not get a suitable destination, a suitable place nearer. Okay. So, that is why I say that a trip will remain as short as possible, right, lengthening only if it fails to find an appropriate destination nearer in hand. If we are not able to find anything nearer, then we will take it further, right. So, we will take those people further. The other example I can give, you can think of like residential choice location, that is again a kind of a distribution model in a way. So, you are working in the city, and most cases there are several cities, say for example, Bombay or Mumbai or say Kolkata. If you take such cities, ideally what people would like to do, generally speaking, if possible people would like to stay in that same building itself, that maybe third floor is the office and people would like to stay in the fourth floor. But people can't stay. Why? Because it is so expensive that people most cases will not be able to afford. So, now just think they can stay anywhere along a suburban line, right. In abroad maybe metro lines are also connected like that, right. So, people will probably find out some location in the suburb, right, and then stay there and commute to office. Now, obviously, if they can stay somewhere nearby, so maybe the main station which is at the CBD end, they would probably like to stay somewhere maybe just which is 4 station away from the main station, right. And if they cannot get a location, then only probably they will think of going to a station which is 5th station or 6th station or 7th station, right. And as you move further, actually you are travelling from a distant place, right. So, the trip length is increasing. So, ideally people would like to locate themselves nearer as possible. So, that means a trip will remain as short as possible in exactly in the same manner, lengthening only if it fails to find an acceptable destination near in hand. You want to stay probably, but you have to find a suitable accommodation there. If you do not find it, you say okay, let me go little far. You still do not get there, then again you travel some more distance, maybe another 1 or 2 stations in the suburban line away from the CBD. So, that is the basic premise. So, assumptions are the number of trip interchanges is directly proportional to the number of opportunities at the destination zone. So far in the gravity model, what we said, the number of trip interchange is directly proportional to the attraction of that zone, right. Here something very similar, but we are saying it is the number of opportunities proportional to the number of opportunities at the destination zone. Say giving this example of working in the CBD and locating a residential location somewhere in the suburb, of course, where higher chance of settling down or finding a residential place, obviously, if there are more housing opportunities, say just imagine near a suburban railway station, lot of new housings have come up and you can easily get probably a flat in rent. Obviously, where more such flats are available, more opportunities are available in general, I am speaking in that given context, more will be that more trips will terminate there, right. So, the number of trip interchanges is directly proportional to the number of opportunities at the destination zone. More the opportunities in the destination zone, more trips are likely to get terminated there. Second, it is inversely proportional to the number of intervening opportunities. Now, somewhat similar to gravity model again, but also different in some sense, right. What is similar? Because there we say inversely proportional to distance or cost or time. Here we are not saying directly inversely proportional to cost, time or distance, but we are saying inversely proportional to the number of intervening opportunities. That means what? It is another way of measuring indirectly, as we were saying the deterrence we were trying to say estimate or trying to quantify in case of gravity model. Here we are in the same manner we are trying to say what are the opportunities in between, intervening opportunity, inversely proportional. That means probably you are more likely to you are getting settled maybe in the 5th suburban station from the CBD. So, what will be your probability or chance that you will get settled down in the 5th suburban station? That will inversely get proportional to the number of opportunities in between. That means, how many opportunities are there in 1, 2, 3 and 4, right, or considering the 5 also, that will decide that what is the probability of you locating in a catchment which is around the suburban station 5. So, that means, if I have more opportunities in between, then I have less chance that I will go up to suburban station 5. So, that is think that in between, if there are lot of new housings coming up, naturally instead of going to zone or station 5, people will probably try to settle down more, or more people will settle down probably in zone 3 or zone 2, right, wherever such opportunities are coming up. So, we can easily say the number of trip interchange is directly proportional to number of opportunities at the destination zone and inversely proportional to number of intervening opportunity. Just think that the same example, maybe I could, that is what I could remember now, maybe there are so many other examples can be given, that you are trying to locate yourself. What is the chance that you will locate yourself in the 5th suburban station? It will depend on how many opportunities are there in the 5th suburban station. The more the opportunity, the more likely that trip will terminate there, and also it will depend how many opportunities are there in between, intervening opportunity. That means, how many housing opportunity will be there in zone 1, in station 1, station 2, station 3, station 4, and naturally if more opportunities are there, then people would like to locate themselves closer as possible. So, then there will be less chance or less number of people will actually go and settle down in suburban station 5. So, very logically we can understand or we can relate such kind of things, right. Mathematically we can write then Tij is proportional to Aj. What is Aj? Aj is the total number of destination opportunities at destination zone J, proportional to that, and inversely proportional to intervening opportunity. So, what is inversely proportional to Vj, where Vj is the number of intervening destination opportunities between zone I and zone J. Remember, we are talking everything this I and J in order of distance, that is the catch of it, and that is very, very important when you are talking about this intervening opportunity model. It just zone 1 is closer, then zone 2, then zone 3, then zone 4, then zone 5, something like this, right. In order of the distance, in order of distance. So, that is what is very, very important, and of course, k is a proportionality constant. Why? Because this will ensure that all trips with origin zone as I are distributed to destination opportunities, proportionality constant. So, that is what is the general formulation. Now, Snyder proposed some modification of the Stafford hypothesis, and we are not going into details, it is not within the scope of the present lecture maybe, but what was shown that the probability that a trip will terminate in some volume of destination points is equal to what? The probability that this volume contains an acceptable destination. That means, I was giving you about the example of 5th suburban station. So, what is the probability that a destination can be found out in around that 5th suburban station times the probability that an acceptable destination closer to the origin of the trip has not been found. Means what? Multiplied that the probability that a destination could not be found out in suburban station 1, 2, 3 and 4. Okay. So, we can write like this: probability of dV, dV you just consider a band or a ring, right, around the production zone I. We can consider many rings around I, and as the I or j is increasing, that means they are going away or the distance wise higher, time wise higher from zone I, right. So, just consider a small ring of dV at a distance v from the origin zone I. Okay. So, then as I said, it is what? It depends on two things. One is that probability that an acceptable destination closer to the origin of the trip has not been found out. That means, we can say 1 minus probability of v, because at a distance v, the small band or ring of dV exists. Okay. So, v within this v, what is the probability that a destination could not be located? That is 1 minus probability of v into L dV. So, probability of dV is what? First it is that the probability that a trip will terminate when DV destination opportunities are considered, and probability of V is that the cumulative probability that a trip will terminate by the time V such rings or V such possible destinations are considered in order of distance or time. So, you can see I is the center, and around that at a distance V, in between there are V destinations, and then you are considering the DV destination just outside V. Okay. So, V is the cumulative total of the destination already considered, and L is what? A constant probability of a destination being accepted, right. So, for that is, so what we said, I am trying to repeat it again in a slightly different form, not very different. The probability of locating within DV opportunities being considered, the probability of locating within DV opportunities being considered is equal to the product of the probability of not having located within the V opportunities, 1 minus probability of V, that is what is said, the same thing, and the probability of finding an acceptable location within DV opportunities, given that a location has not been already found out. So, into L DV. Snyder also has shown that probability of V can be expressed as 1 minus k I into e to the power L V. The L V all meaning remains same. K I is what? K I is a constant for zone I to ensure that all the trips produced at zone I are distributed. You can relate it very easily with various types of trip distribution model I mentioned once again today in the beginning, right. Unconstrained model, and then production constant model, attraction constant models. Okay. So, these are basically bringing back all those things. Now, the trip interchange between I and j is given then by this formula T I j equal to P I, total trips produced in zone I, into what is the probability that a trip termination will happen in zone j. Now, we are no more talking about V or dV, but we are talking zone j. Exactly in the same way, you can think of like dV small band, or a small ring away from the production zone I. So, what is the probability of trip termination in zone I? One is the probability of trip terminating in zone j, within zone j, the whole band or whole width or whole distance, minus probability of locating in V into V j minus 1. That means, we have 1, 2, 3, 4 like that, we are talking about the jth zone in order of distance or time. So, what we are saying, probability of V j minus 1 means the probability that a trip will have found a suitable destination in the opportunities already considered up to zone j, but not including zone j. It is actually excluding zone j. What is the probability of locating a trip within that distance or within that many zone? So, number of zones will be what? J minus 1, because we are not including jth zone, and probability of V j will be what? Same thing, the probability that a trip will have found a suitable destination in cumulative opportunities considered up to and including j now. The earlier one excluding j. So, up to jth zone this case, and previous one the probability of locating a trip up to zone just outside J up to that, excluding Jth zone. So, up to J minus 1th zone, that is what it is. So, that is the difference, cumulative probability difference in cumulative probability, that the trip will terminate in the Jth zone or Jth ring or Jth band, whatever you say. Now, considering that probability of V equal to 1 minus k I into e to the power L V, that way if you put, then you can put T I j equal to k I p I e to the power minus L V j minus e to the power minus L V j minus 1. Now, applying the production constants, if we apply the production constants, means what? T I j sum over j should be equal to p I, that is what let us do. Then in that case what you find? K I into p I into e to the power minus L V j minus e to the power minus L V j minus 1, right, equal to p I sum over this equal to p I. So, then what you find? You get p I will be there, p I will cancel, and then you get k I equal to 1 by 1 minus e to the power minus L V n. Why you are getting 1? Because you say 1 to 2 and then 3, then 4, right, sequentially it is coming. So, the term will cancel out and you will finally get only what will remain, 1 minus e to the power minus L V n, okay. Because all intermediate zone you can see here e to the power minus L V minus e to the power L V j minus 1. So, what will be the earlier one? E to the power L V j minus 1 minus e to the power L minus L V j minus 2. So, plus minus will get cancel out for all zones, right. So, what will remain is only 1 minus e to the power minus L V n. So, here you can find out the value of k I. So, once you have got this, that is the equation you get as it is shown here. So, this is a forced intervening opportunity model, which is singly constraint model, production constant. So, singly constraint, and because this is constraint, so it has to match the production. So, you can also call it as forced intervening opportunity model. If you add another constant instead of the constant that all trips will be made, then you get free intervening opportunity model. So, what will happen? That k term will not come in the previous one. What we say? That k term will not come into picture, right. So, it will be simply p I e to the power minus V j minus 1 minus e to the power L V j. This k equal to 1 minus e to the power minus L V n, that V j, that will not come. This is called me as free intervening opportunity model. That means, this production attractions will never match, right. They will not match, even the total number of trips also we are not forcing, right. Let us take an example. I have given 3 zones here, trips produced in these 3 zones, trip attracted to this 3 zone, and then order of closeness. Remember, this order of closeness is very important in this case, right. So, what is the order of closeness? Like the column indicates, the first 1 to 3 indicates which is the what is the closeness of zone 1. So, 1 if you consider, the closest zone is 1, then next is 2, next is 3. For zone 2, the closest one is actually 2, then 1, then 3. 3, the closest one is 3, then 1, then 2. That is the order of preference, and here it is the L value for zone 1, zone 2 and zone 3. Now, if we want to try to distribute this thing, let us clearly understand this part. This is the very important component, otherwise you will get confused. So, for let us say example, we want to explain you the trip interchange between 2 and 3. So, from 2 up to 3. So, with 2 as origin, zone 3 stands where? Zone 3 is, so first closest point intervening opportunity, closest to 2 is what? First 2, then what? 1 as you can see, and then 3. So, the intervening opportunity up to, if you are saying zone 3 means V j minus 1 means not including zone 3. So, up to zone 3, but not including. So, up to zone 3 what will be there? Zone 3 is the third zone in order. So, before that, just before zone 3, zone 1, and just before that zone 2 itself. So, attraction of zone 2 and zone 1 will be there 40 plus 30. Then up to zone j means along with this we are talking about zone 2 to zone 3. So, j minus 1 whatever you got earlier, now the jth zone, that is the zone 3 also will be added. So, attraction of zone 3 also will be added. So, you just simply add now also 25 with that. So, 40 plus 35 earlier up to V j minus 1, and V j will be 40 plus 30 plus 25. That clearly explain the whole thing. So, like that, if you consider the trips attracted 35, 40 and 25. So, order of closeness of the zone, I have just reproduced it from the previous one as it was given originally, so that you understand clearly. Then two things I am showing here. For each origin zone and for each of the destination zone j, each origin zone I, each destination zone j, considering the order of closeness, what you will consider when you consider up to V j minus 1, and then what you consider when you consider up to and including jth zone. The basis is exactly same as I have explained earlier for one element from 2 to 3, exactly the same way I have shown the value, that what you can opportunities you should consider when you talk about up to j minus 1, that means up to j, but not including jth zone in order of closeness, and when what you would consider up to V j, both I have shown. So, accordingly once you have done that, then this basic equation is known, remaining thing is not so complicated. The only complication is that order of closeness, and accordingly to understand clearly what are the zones and their opportunities I should include in what calculation, which I explained clearly in the last two slides. So, here you will use the equation T I j equal to P I into e to the power minus L V j minus 1 minus e to the power minus L V j. It is unconstrained. So, we are not putting any constraint. So, accordingly you calculate T 1 1, T 1 2, T 1 3, and like that 2 1 2 2 2 3 3 1 3 2 3 3. Okay. Remaining calculation is very straightforward. And here also I have said then from the previous one, I have borrowed the this two tables, what showing that what you really need to consider as the opportunities when you are talking about various j's, and then opportunities up to j minus 1 and opportunities up to j, and up to means including j. Those tables are also referred here, so that easily you can understand, right, how the calculations are being done. So, now if we see that trip distribution matrix, what we find here, attraction wise zone 1 25, zone 2 24, 30 and 79 is the total number of trips. That means, we wanted to distribute 100 trips, but because this is unconstrained model. So, how many trips have been distributed? Only 79 instead of 100. So, all trips have not been distributed because it is unconstrained model. So, model automatically will not ensure that, but then shall we leave it like this? No, we shall not leave it. So, what we can do? The answer is again simple and known to you. You remember singly constrained gravity model, when we took the production constraint models, the attractions were not matching. So, what we did? We want this attraction to be this, when we target this, we got this. And that same example, you want 80, when you target 80, you get 70 marks. So, what does it indicate? You should then target 90 or more than 80 definitely, right. More than 80 you should attempt, target, then probably you will end up getting somewhere around 80. But if you only target 80, you are not going to get 80. Okay. So, same kind of thing I have shown you earlier when I talked about how these adjustments are required to be done for singly constrained gravity model. The same way you can do it here. So, I have only shown you the formula. The design totals may be further adjusted using the following formula. So, now you will think that my attractions are different, modify the attractions, and then exactly productions will not change, order of closeness will not change, the procedure for calculation will not change, but with the revised attraction values what we used in this model. So, the revised attraction values will come. So, what you will get here is basically the target will be different, right. And then with this revised target, you will modify your target as I have shown you there. And remember that a model could be, you can think little carefully, a model could be production constraint model, a model could be attraction constraint model, what kind of model, and accordingly you have to keep the do the adjustment. Here also similar kind, the target could be different, right. So, accordingly the procedure will not change, the way the order of closeness will not change, but the other things will change. I am showing you AJ values, what AJ values you have used. So, this AJ values you need to modify, okay, and then do iteration, and maybe 1, 2, 3 iterations you need to do, and then finally, you will get something which will ensure that you have actually distributed all the trips, right. And with this, I would say some of the advantages, as you know that intervening opportunity model distribute trips according to measure of bypass opportunities or consider the intervening opportunities. Distance is used as a ordinal variable, and then the this has got a logical basis consideration, as we gave you an example, right, that fifth station, or if there is a natural calamity, you want to shift people, you want to shift to nearby area only, right, which is safe. Of course, if it is possible and there are opportunities, you would like to shift them nearer rather than shifting to a far distant place, right. So, there are limitations as well, as I said, the data with the destination ranked by distance from origin is more difficult to handle in practice, because the order is very important, and not like a simply any ij give the distance and I will use a gravity model, that kind of thing you cannot do. So, this order closeness is very very important, and sometimes it is confusing as well and difficult. So, in the calibration and application of the model, the highway network is only implicitly used, we are not directly using the travel time or so, but yes, indirectly there are consideration that we are talking about intervening opportunities there in some form or other we are considering. can't reflect the change in the roadway infrastructure. You cannot say simply I modify the transport network, how it is going to change, and generally gravity models are found to perform better than this intervening opportunity model. So, altogether what we discussed here about the types of trip distribution model and in details about the various aspects of intervening opportunity model, including an example and talking about their advantages and limitations. So, with this I close this lecture. Thank you so much.